Namaste. In today's class, we shall look at some methods of distance measurement, especially foot, tape and rangefinder. So, what do you do when you get into a forest and you do not have any instrument and you want to measure some distances, say the distance to the next tree. So, can we use some parts of our body to do that? Well, the answer is yes. We take one step to be 0.7 meters. So, for instance, if I had to measure the distance from this point to the end of the wall, I would just walk from here to the end of the wall and just count the steps 1, 2, 3, 4, 5. So, when we have 5 steps, it means that the distance is 0.7 into 5 or approximately 3.5 meters. So, this is when we do not have any instrument. Now, what is the simplest instrument that we can carry with us at all times into the forest to take measurements? That would be the tape. So, as we have seen in a previous class, we can use a tape to take measurements along the ground, as this forest guard is doing in this picture. So, he is holding the tape in his hands. One end of the tape is fixed to the point from which he wants to take the measurements. Then this tape goes on rolling and he can take the measurements using the tape. One other instrument that is being very highly used in forestry is the rangefinder. So, this is the picture of a rangefinder. Now, how does a rangefinder work? This rangefinder will, suppose this is your rangefinder and this is your tree. So, this is the point to which you want to take the measurements. And suppose you are standing here with a rangefinder in your hands. So, how would this rangefinder measure the distance? It would give out a ray of light. So, it is a laser, right? This light would go interact with the surface of the tree and then get reflected back. Now, this rangefinder would measure the time t between the emission of a pulse to the time this pulse comes back. Now, when this ray of light is going from the device to the tree and back, so it is covering a distance that is equal to d here when it is going towards the tree, and also another distance d when it is coming back. So, the total distance is equal to d plus d or 2 times d, where d is the distance between the tree to the point where the observer is standing, and the time taken for light is equal to t. Now, we know that the speed of light c is equal to 299,792,458 meters per second, or approximately it is equal to 3 multiplied by 1, 2, 3, 4, 5, 6, 7, 8, 3 into 10 to the power 8 meters per second. So, now the distance is equal to speed into time, which implies that the distance is 2d. So, 2d is equal to the speed of light c multiplied by the time t. So, this would give us that d is equal to c times t by 2. Now, c is a constant, t is something that your rangefinder measures. So, you can calculate d from here. So, that is the theory of using this rangefinder. So, now we will come to a demonstration of a rangefinder. We shall not be using a laser rangefinder, but we shall be using an ultrasonic rangefinder. So, let us now have a look at how a rangefinder works. So, this is a rangefinder, this is an ultrasonic rangefinder. So, it has got 2 ends. So, one end gives out ultrasonic pulses, they interact with the object in front of it and then they get reflected back to the instrument, and the time that is elapsed between the emission of a pulse to this pulse coming back to the device is used to get an idea of the distance of the object from the instrument. So, for instance, if we keep it close to the object, so it is giving us these sound signals at a very fast rate. So, that is telling us that the object is very close by. If we increase this distance, this pulse decreases in time. So, let us now have a look at the code. Let us now have a look at the code. So, we have in this code we have defined our trigger pins. So, because this device is connected to Arduino, so we have defined its trigger pins and the echo pins. We have also defined a buzzer pin and a beep frequency and a beep time. So, when we initialize this code, so we set up a serial communication in this port 9600, then it goes into the loop. In the loop, we have defined our variables as duration, inches and centimeters. The sensor is triggered by a high pulse of 10 or more microseconds, and then it is and we give it a short low pulse beforehand to ensure a clean high pulse. So, as we can see here, we have set the pin mode of the trigger pin as output. So, we first set this output to low for 2 microseconds, then we set it to high for 10 microseconds and then we set it to low again. Now, because this portion of the code is in the loop, so it will go on repeating it again and again. Then it will take the signals from the sensor, a high pulse of whose duration in time in microseconds, from the sending of the ping to the reception of its echo of an object. So, in this case we have set the pin mode of the echo pin as input. Now, duration is the variable that we had defined before. So, it is a long variable. So, duration is the pulse in for the echo pin and high. So, it will measure the time for during which the echo pin is set to a high. Then it will convert this time into a distance. So, we can measure these distances in inches or in centimeters. So, let us look at the centimeters part. So, we have defined a function here, microseconds to centimeters, and we give it an input as the duration. So, now let us have a look at this function. So, here is our function long microseconds to centimeters, which takes an input variable in long microseconds. So, the speed of the sound is 340 meters per second or 29 microseconds per centimeters. This ping travels out and back, and so to find the distance of the object we take half of the distance travelled. So, to travel 1 centimeter it takes 29 microseconds. So, how many centimeters will it travel in 1 microsecond? It will be 1 by 29. So, if we take these microseconds, which is the input variable for the time elapsed between the emission of the pulse and its coming back, if we divide it by 29, we get twice the distance from our device to the object, and dividing it by 2 will get the distance of the object from the device. So, once we have converted it into this time duration of microseconds into centimeters, we can ask our device to give us a serial output of distance in centimeters, which will be given as centimeters, and then we give it a short delay, and then this loop goes on again and again. So, let us now have a look at how this distances would appear. So, now in front of our device we keep a book which will act as a reflector. So, the ultrasound pulses will that are emitted from the device will go and interact with the book, and then they will go back to the device, and we can change this distance of our book from the device. So, I will keep it close to the device, and then I will go on extending the distance. So, now let us have a look at what distances are being measured. So, if we go to the screen now, we can see that it is giving out a distance of 5 or 6 centimeters. So, if we wanted to measure its distance, we could take these values 5 and 6 and then take out an average. Now remember that because this is a physical device and we are taking the measurement of a physical parameter, we will not be getting an exact distance, but every time that we measure this distance we will be getting some value, and the average of these values would be the correct value. So now let me take this device, this book away from the device. So now it is measuring it to be 11 or 12 centimeters. If we extend its distance further, now it is measuring 16 to 17 centimeters. Again extending it further, now it goes to 20 or 21 centimeters. So this can measure any distances up to a maximum. So for instance, it has now gone to 40 centimeters. So now it has gone to 40 centimeters here. We can go on extending it, but now its accuracy will go on decreasing, and after a while it is not getting any signal back from the book to the device. These signals are getting lost, and so it is not able to measure the distance. So every device has its own range. So this rangefinder can measure till a few centimeters, but if we used a laser rangefinder, it would be able to measure till many meters. Now let us look at something different. So now I am, if we focus on the book now, so in front of our device I have kept the book. Now what will happen if I tilt this book so that the signals, they reach this book and then they are reflected out to some other location. So let us now have a look at the screen now at the distances. So it is showing me as 20 centimeters. Now let me tilt this book. So it went to 170 centimeters. So if we looked at the book now again, so I am just turning it from here till here. So I am not changing its distance. So let us move back to the screen now. So when it is kept vertical, it is showing me as 20 centimeters. When it is deflecting, it has gone to any arbitrary value, 200 plus centimeters. So it is some value that it is unable to measure. So it is giving it as any arbitrary value. So this was 20 centimeters and this is some arbitrary value. So why does that happen? So if we now looked at the tablet, so our device, so it is giving out a pulse that is going to the object, and this pulse, when it returns, it takes the time t and then calculates distance as 2d is equal to t times the velocity. Now what happens when I tilt this book? So when I am tilting this book, then these rays of, then these pulses, they are going and then they are getting reflected to some other point. When they get reflected and this device is not getting any pulse back, so it is unable to calculate this value t. This t comes to be some large value, and so it will measure this distance, d is equal to t times v upon 2. When t becomes some large value, this d will also become some very large value. Now this phenomenon in which your beams are getting reflected to some other location is also used in the case of stealth devices. So for instance, if you had an aeroplane and if you had a radar, the radar also works on a very similar principle. So any beams of microwaves that are emitted, they interact with your device and then they are reflected back, and these reflections are then measured by your radar to get the position and the speed of the object in front. What if this device, in place of having a very smooth surface that was able to reflect these waves back, had very sharp surfaces that were at some other angles? So for instance, suppose it had a surface like this. So what would happen would be that this radar beam, it went to the object and then it got reflected somewhere else. So, this device will not be able to get the signal back, and when it does not get any signal back, what it senses is that there is no device in that is there is no object in front of this device. So, this is used in stealth planes or for other stealth applications. But why do we need to keep this point of the stealth planes in mind in the case of forestry? So, now suppose we have a tree and we are standing on the ground and we use our rangefinder here. So, it is giving out some pulses which will then interact with the tree and they will get reflected back and they will then be measured by the device. But in the case of a leaf, so a leaf gives it a flat surface. Now, in the case of a leaf, if we consider its lamina, so if this is a leaf and this is a flat surface, also known as the lamina or leaf blade. So, now if our signal interacted with this lamina, so if our signal interacted with this lamina and it got reflected to some other location, then probably our device will not be able to get the correct distance of the device from the tree. So, this is one source of error that we get in the when we are using the rangefinders. So, how do we solve this error? Will we take multiple readings? So, because we have a number of leaves here, we will take multiple readings and will then average out those readings. So, now this is where your averaging comes into play. So, sum of distances divided by n. So, suppose you took 10 readings. So, you get 10 distances, you sum them up and then you divide them by 10 to get an average. And because an average is also affected by the extreme values, so suppose you got readings as say 10 meters, 10.1 meters, 10.2 meters, 9.9 meters, 9.8 meters, 10 meters, 10 meters, 10.1 meters and say 200 meters. Now, if we considered this value of 200 meters, it would, so these are 9 values. So, let us take a 10 value. So, 10.2 meters. So, if we considered this value of 200 meters, it would deflect our average by a lot. So, whenever we are taking readings with the rangefinder, we should take a number of readings, then we should exterminate these extreme values and then take the average to get the correct distance. Now that we have seen the demonstration of the rangefinder, let us now look at a few examples. So, this is the example as you can see on your screen. The top of a tree is at a distance of 50 feet and the tree itself is at a distance of 40 feet. If the instrument is kept at a height of 5 feet, find the height of the tree. Now, essentially when you are using a rangefinder, it can not just be used to measure the distance parallel to the ground, but it can be used to measure any distance. So, for instance, you can take the distance from this point to the top of the ceiling or to the wall or to the front or anywhere. So, using that, how can we calculate the height of the tree? Now, in this problem we are given that we have a tree, there is an observer holding a rangefinder in his hands. This rangefinder is at a height of 5 feet from the ground. The observer uses the rangefinder to take this distance. So, this distance let us call it, let us make a triangle out of it, A, B, C, D and E. So, we are given that BC or ED is equal to 5 feet. The top of the tree, that is A, the point A is at a distance of 50 feet. So, we have AE is equal to 50 feet and the tree itself is at a distance of 40 feet. So, we have BE or CD is equal to 40 feet. We need to find AC. Now, how do we go about doing that? In triangle ABE, so we are considering this triangle. So, in this triangle we have this angle is 90 degrees and this is a right angled triangle. We have AB is unknown, BE is given as 40 feet and AE is given as 50 feet. So, can we calculate AB using these values? Well, yes, we can calculate that by using Pythagoras theorem. So, because this is a right angled triangle, we have AB square plus BE square is equal to AE square, or AB square plus BE is given as 40 feet. So, 40 square is equal to 50 square. Now, 40 square is 1600, 50 square is 2500. So, you will have AB square plus 1600 is 2500, which would give us that AB square is 2500 minus 1600 is equal to 900, or AB is the square root of 900 is 30 feet. So, we know now that this distance AB is 30 feet. This distance BC is equal to 5 feet. So, the height of the tree, height of tree AC is equal to AB plus BC is equal to 30 plus 5 is 35 feet. So, just by using a rangefinder and measuring two distances, one is this distance, the second distance is this distance, and knowing the height at which the rangefinder is kept, which can also be measured using the rangefinder itself. So, just by using these three distances, we can calculate the height of the tree. So, this is how it would look. Using Pythagoras theorem, we calculated AB to be equal to 30 feet, this should be feet, and the height of the tree is 35 feet. Thank you for your attention. Jai Hind.